Good morning, I am Fabio Rondinella and I am a PhD student at the University of Udine. The title of my presentation is Dynamic Modulus and Phase Angle Predictions of Asphalt Mixtures, a comparative analysis of single and ensemble machine learning algorithms. Road pavements represent the backbone of every road network. The main technological solutions for road pavement construction are flexible and rigid, with the flexible being the leading one. Flexible pavements are usually prepared with aggregate, filler, and bitumen, and by virtue of this, they show a traditional viscoelastic behavior that can be characterized by means of a performance parameter named complex modulus. Case study regards an experimental trial that took place at the Technical University of Vienna, where 9 different asphalt mixtures were designed, produced, and tested to receive data on their viscoelastic response. Details about their grading curves are provided in this figure. For surface layers, AC11, SMA11, diabase was used as fine and coarse aggregates, while for binder and base mixtures, AC22, AC32, limestone was the choice. In all cases, the filler was powdered limestone. Unmodified as well as polymer-modified bitumens were used. An extensive 4-point bending test campaign was carried out to determine complex modulus values, expressed in terms of dynamic modulus E star and phase angle phi. Tests were performed in displacement-controlled mode at temperatures ranging from -15 to +45 Celsius degrees, and a frequency sweep from 0.1 to 40 Hz at each temperature. For each mix, at least 3 single specimens were tested, resulting in 1,680 observations recorded, but the results used in this study are mean values from the single tests, with a total number of records equal to 560. As shown in this figure, on the basis of time-temperature superposition principle, master curves for AC11 up left, AC22 up right, AC32 down left, and SMA11 down right mixtures were realized with a reference temperature of 15 Celsius degrees. The methodology followed in the present study can be summarized as follows. Materials were characterized and each mixture was prepared with the optimum binder content. They were compacted and their performance was evaluated in terms of dynamic modulus and phase angle. Several machine learning models were developed, trained, and tested in order to predict dynamic modulus and phase angle values, and a comparative analysis between these models and some well-established empirical equations was carried out. Finally, the main conclusions were drawn. Wichak-Fonseca and Wichak-137A empirical equations were implemented in the developed methodology as a comparative term. Here, dynamic modulus values can be determined as a function of grading curve parameters, air void percentage, effective bitumen content, loading frequency, and asphalt viscosity. The latter is determined as a function of two constants, A and BTS, and the Rankine temperature. Machine learning approaches were used to model the mechanical behavior of the investigated mixtures in terms of dynamic modulus and phase angle, on the basis of the same input features implemented in the empirical equations just observed, plus a categorical variable distinguishing the aggregate nature. This is a problem of machine learning regression, and consists in finding a function that approximates mapping from an input domain to real numbers based on a training sample. 3 of the most common algorithms to accomplish this task are support vector machines, artificial neural networks, and decision trees. Support vector machines map the input variables to a feature space and are aimed at finding the hyperplane that maximizes the margin between it and the closest data points, also minimizing the prediction error. If data are not linearly separable in the original space, then some transformations can be applied in order to map the data from the original space into a higher dimensional feature space. This practice is known as kernel trick, and most common kernel functions were evaluated, namely linear, polynomial, radial basis function, and sigmoid. An artificial neural network model is the result of simple units, the artificial neurons, organized in layers and connected through biased and weighted connections. The first layer is called the input layer, and it is composed by a number of neurons equal to the number of features of the feature vector. One or potentially more hidden layer follows the input, and each neuron activity is ruled by a particular activation function. Here, computational processes take place, and model computing power is determined by its number of neurons. The last is called output layer, and it returns the outcome of the network. A decision tree is a tree-like structure where each internal node tests on attribute, each branch corresponds to attribute value, and each leaf node represents the final decision or prediction. Specifically, categorical boosting algorithm was introduced in 2018. Basic predictors are oblivious decision trees, resulting in a more balanced architecture, less prone to overfitting, and significantly faster during the test phase. CatBoost allows categorical features to be automatically handled and processed, and text to the ordered boosting avoid some typical gradient boosting drawbacks, like prediction shift and target leakage. 6 goodness of fit metrics were selected and implemented in order to evaluate the performance of developed models as accurately as possible. Their mathematical formulation was reported. Specifically, they included mean absolute error, mean absolute percentage error, mean squared error, root mean squared error, Pearson correlation coefficient, and the coefficient of determination. A comparative analysis was firstly carried out in terms of dynamic modulus in order to include also the empirical equations. It can be observed that Wichak 137A performs significantly better than Wichak Fonseca, and also slightly better than sigmoidal SWM and linear SWM. Radial basis function SWM and poly SWM improved the resulting performance metrics, but state-of-art artificial neural network and CatBoost achieved outstanding results with ANN performing slightly better in terms of root mean squared error, and CatBoost performing slightly better in terms of mean absolute error. However, the higher interpretability of CatBoost model makes it preferable. Focusing on CatBoost results, feature importance algorithm was introduced to determine how much CatBoost predictions change on average if the feature values change. Feature importance values were normalized so that the sum of them could be equal to 100%. To predict dynamic modulus and phase angle, temperature more than 40%, binder viscosity roughly 35%, and loading frequency roughly 8% were more critical than empirical regression constants, volumetric properties, and aggregate nature, roughly 15% altogether. To obtain further insight into the CatBoost predictive capabilities, the comparison between the experimental targets and the outputs predicted by the model are here provided in terms of dynamic modulus. In this histogram graph, test values are shown in black, while the respective CatBoost predictions are shown in gray. The horizontal axis identifies each of the 112 dynamic modulus values that make up the test set. It can be appreciated that the predictions are very close to the observed experimental data. Also, CatBoost phase angle predictions are always close to the real target values for each of the 112 test observations. Such findings are significant from an engineering perspective because they highlight the reliability of the developed model and demonstrate how accurately and simultaneously this model can predict two fundamental parameters for asphalt mixture mechanical characterization. To get an even deeper understanding of CatBoost predictive performance, regression plots related to E star on the left and phi on the right are shown. The 45-degree blue solid line represents the line of equality that reflects 100% accurate predictions, while light blue circles represent CatBoost actual predictions. Predictions do not strongly differ from the line of equality, confirming the remarkable results described by Pearson correlation coefficients roughly equal to 0.99. A Shapley additive explanation analysis was also performed on CatBoost model outputs. Skipping the mathematical discussion for time constraints, such technique was implemented to understand why the model made certain predictions, thus focusing on the concept of prediction interpretability. Shap values assign to each feature an importance value for a particular prediction. Moving from top to bottom, the variables can be read in rank order. Moving from left to right, a smooth transition from blue to red stands for a direct proportionality relationship between the target and the specific feature, while a transition from red to blue stands for an inverse proportionality. In conclusion, the present study was aimed at outlining a detailed methodology in order to implement some of the latest and most innovative single and ensemble machine learning algorithms for the simultaneous prediction of both dynamic modulus and phase angle of 9 different asphalt concrete mixtures. Variables required as input by the predictive models can be easily determined during a preliminary mix design procedure or derived from them, minimizing laboratory technicians' effort required. The developed models are capable of simultaneously providing reliable predictions of both dynamic modulus and phase angle, especially with respect to state-of-art artificial neural network and categorical boosting models. This would reduce the need for additional expensive and time-consuming laboratory tests to determine them experimentally. In this way, performance parameters such as E star and phi could be easily estimated and then implemented within the most common asphalt pavement design procedures. Every machine learning-based method provided remarkable results. In particular, state-of-art artificial neural network and categorical boosting outperformed both empirical equations and their SWM competitors, and achieved very encouraging and roughly comparable results. However, as explained before, the higher interpretability of CatBoost makes it preferable. The outlined methodology was calibrated on data from the mentioned experimental trial. For future developments, it could be adopted to analyze fatigue and permanent deformation resistance data, in order to obtain an increasingly powerful and high-performing tool. Thank you for your attention.